So, changing gears one more time, just a little bit. I want to finish this off by talking a little bit about energy and angular momentum, two kind of quick quantities that we're going to be seeing come up a bunch of other times throughout the course. This concept of energy, energy is a mathematical property of different kinds of systems. So it's really just a number. But this number is something that if you have a way of calculating that energy, that total amount of energy won't change. Energy can't be created or destroyed. So if I have a system and I know how much energy it starts with, and then it goes through some weird transition, I know it's going to have that same total amount of energy that it had before because energy can't be created or destroyed. If something's going on and some energy leaves that system, I should be able to know exactly how much energy left and how much energy is remaining. Because again, overall, throughout the universe, energy can't be created or destroyed. But it can change between many, many different forms. So the total energy content of the universe is constant. But again, there's many, many different kinds of energy. In fact, let's talk about some of those different kinds of energy. Take a moment and try to pause the video and think of how many different kinds of energy can you think of? Okay, so pause the video. How many types of energy can you think of? Okay. So hopefully you did that. Let's go over some types of energy. There's kinetic energy, the energy of motion. So if I have an object, the faster it's moving, the more kinetic energy it has. We've got this thing called gravitational potential energy. If I take an object and I hold it higher up in a gravitational field, it has more gravitational energy. If I let that object fall towards the Earth, well, it loses that gravitational energy. But let's look at this specifically. So I lift this up in the air, I'm giving it gravitational energy. Let me reset my camera. So I'm lifting this up in the air, I'm giving it gravitational energy. And when I release it, that object starts to fall. And as it moves downwards in this gravitational field, it loses some of its gravitational energy. Does that energy just get eliminated from the universe? And if not, where does that energy go? Think about that for a second. So we start with gravitational energy when it's up here. I release the object and it falls downwards. As it falls, it's losing gravitational energy, but notice it's moving faster and faster. It's gaining kinetic energy. So in this system, when I drop this object, well, it loses that gravitational energy, but it's not eliminated from the universe. It's being converted to kinetic energy. When it hits my hand, well, you can hear a little thud. There's some sound energy that comes out of that. There's some vibrational energy that goes into my arm. So again, energy isn't being created or destroyed. It's just changing between lots of different types. Other types of energy that we're going to be talking about in this course. Thermal energy. If you take your hands and rub them together, I'm trying to move my hands very quickly and friction causes them to slow down. So it's removing kinetic energy and it turns that into thermal energy. It increases the kinetic energy of the atoms in your hands. There's chemical energy, the energy stored in chemical bonds. So for example, how did I get the energy to lift this object up in the air? Well, I had lunch and my lunch is made up of materials that have, various chemicals that my body can break down. And when those chemical bonds are broken and reformed in different ways, they can release different kinds of energy. And that powers my muscles and allows me to lift this up in the air. There's one thing that we're going to be talking about when we talk about the properties of stars is mass energy. This equation that I'm guessing most of you have at least heard of before, E equals mc squared, is that mass in certain conditions can be converted into a huge amount of energy. So this is the energy in a certain amount of mass And this c value, that is the speed of light. Speed of light's a big number. When you square a big number, you get a freaking huge number. So even a small amount of mass, if that's converted to energy, you can have a huge amount of energy output out of that. And this is what's going on in the fusion reactions inside the sun. There's probably other kinds of energy that you might have thought of, things like electrical energy, wind energy, geothermal energy. One that we're going to be talking about in a couple of classes is light energy. So when sunlight comes in and hits you, it starts to warm up your body. Well, that thermal energy had to come from somewhere, and it's actually stored in the light itself. So again, in all of these cases, we can have a situation where energy changes between some of these different types. But again, the total energy content of the universe is constant. So let's see how this comes into play with talking about these orbits. I said when I hold this object higher up in the air, it's got more gravitational energy, more gravitational potential energy. In the same way, if I have a star and a planet, and that planet's really far away, it's high up above that star, then it's got a lot of gravitational potential energy. As the planet approaches the star, if it's got this kind of higher eccentricity orbit, then when the planet gets closer to the star, it's losing some of that gravitational energy. Where is that gravitational energy going? Well, it ends up ending up in this planet as more kinetic energy. It's moving faster and faster. So as the planet kind of, in a sense, falls towards the star, it's moving faster and faster, and that is going to be at its fastest at the perihelion position. It's going to fling around, and then now it's starting to go away from the star. As it moves away from the star, it's losing that kinetic energy because that kinetic energy is being converted back into gravitational energy by the time the planet is on this side of the orbit. So again, there's lots of different cases that you can think of for conservation of energy. It's one of the cornerstones of our understanding of physics. So I think we went through a bunch of examples of energy conservation. Let me just give like one last that kind of relates to this when the planet swings by the star and is now on its way towards the aphelion position. That's kind of like if I gave this object some kinetic energy, if I give it some kinetic energy, it can use that kinetic energy to go higher in this gravitational field. It loses that kinetic energy, but it gains gravitational energy. Eventually, it reaches its peak, can't lose any more kinetic energy, starts to come back down, and now we're back to the converting gravitational energy to the kinetic energy of the system. One last one that I want to look at is this concept of angular momentum. We're not going to worry about this equation, but when I have an object that's spinning, that spinning object has a certain amount of what's called angular momentum. And the amount of angular momentum depends on the mass of the object, depends on what's the radius of the circle that that object's moving in, and how fast that object is moving. And in a lot of the systems that we're going to be looking at, this angular momentum is conserved. But this leads, if this whole thing is constant, for a circular orbit, the mass is always staying the same. The radius, if it's a circular orbit, it's always at the same radius. So if all of this multiplies out to a constant, we're going to be having the same velocity the entire time as well. But on the other hand, what if I have an elliptical orbit? Well, if this whole quantity is conserved, if this is always going to equal the same thing, the mass times the radius times the velocity, when the radius is very, very large, that means I'm going to have a small velocity. When the radius is much smaller, if this all multiplies out to the same value, the velocity has to be much, much higher in that case. this is the source of Kepler's second law. That whole sweeping out equal areas in equal time, that is a direct result of this angular momentum concept. This is kind of the foundational concept that results in Kepler's second law. So let's actually try to simulate this rather quickly. I didn't think I was going to do this, but let's give this a try. I'm going to try to simulate this kind of whole conservation of angular momentum thing by taking some masses. I'm going to pause this to get my screen set up. Okay, so I'm going to try to give a quick little demo of this conservation of angular momentum concept, because again, the idea is if I have a rotating system, if there's more mass further out, it's going to rotate slower. If more mass is further in, that's going to cause it to rotate faster. This conservation of angular momentum concept is going to cause that to spin a lot faster. So I'm going to try to simulate that with a couple of masses. I'm going to get on my chair and try to spin myself around, starting with these held out, and then I'm going to pull my arms in, and we're going to see what happens. Hopefully I can do this without falling over. So I'm spinning around with these out, and I'm going to pull in 3, 2, 1. Okay, how long can I hold that on? A moment, please. I'm very dizzy right now. So what was happening there is when I took those masses and I pulled them in, it's the same thing that causes a figure skater to spin a lot faster when they pull their arms in. That mass being pulled in, conservation of angular momentum demands that the object is going to be spinning faster. So let's look at what happens when we take all these ideas and put them together. Okay, the room's no longer spinning for me. So let's take these ideas of conservation of energy and conservation of angular momentum, and see if we can put them together to think of what's going to happen to a cloud of dust and gas in space when gravity starts to pull all that material inwards. Okay, so we're going to start imagining this. Let's say I've got this giant cloud of dust and gas in space that, just due to random motions, might be slowly rotating. At the beginning, all this stuff is really, really spread out, so it's got a lot of gravitational energy. Okay? So when gravity starts to cause this thing to collapse, a couple of things are going to be happening. First, it started with this very, very slow rotation, and as gravity pulls that material inwards, that material is going to start rotating faster and faster. So as the material gets pulled in, it's going to be spinning faster and faster. We also are saying we're starting with lots of gravitational energy, and as that material gets pulled in, well, that gravitational energy is going to be converted into other forms of energy. At first, it's going to be kinetic energy. Those gas clouds and dust clouds are going to be moving faster and faster, but eventually, as they get closer and closer together, those gas clouds are going to start rubbing against each other, running into each other, and it's going to convert that kinetic energy to thermal energy, which means it's going to start to heat up. So again, we've got this spinning cloud of gas. It's starting to pull that material in. Gravity's pulling that material in, and it's starting to heat up and spin faster. Most of that material is going to fall right to the middle and heat up a lot. Some other little bits of that material might end up kind of spinning around and starting to clump together on its own. And notice we're already making a pretty decent solar system. That majority of the mass that falls in towards the center, that's going to be a star. It's heating up. Eventually, it'll be the right conditions for fusion to initiate in the core. And the spinning stuff that didn't quite fall in, well, that's going to be the seeds of planets. That's going to be the precursors to planets, asteroids, comets, things like that. So the point that I want to make here is these ideas in terms of conservation of energy, Newton's laws, angular momentum. These concepts are going to be coming up again and again throughout the course. So when we eventually get to talking about the finer details of things like star formation, or the properties of stars, properties of galaxies, things like that, these ideas are going to keep on coming up. So we'll call that good for this session, and hope everyone's doing well.